Hi all. Yeah, I'm here to present our work SIMC, that is ML Inference Secure Against Malicious Clients at Semi-Honest Cost. I'm Akash, and this is a joint work with Nishanth, Divya, and Bhavana. This work is in the problem of secure ML inference. Here you have the two parties, the server and the client. The server holds the ML model M and weights W, and client holds the input vector X. The two parties then interact in order to allow the client to learn the inference output. We want this security guarantee from the interaction that the server learns no information about the private input of client, and client learns only the inference output. This actually can be realized through secure multi-party computation, which is a classic cryptographic technique. One of the applications of secure inference is in the domain of health infrastructure. Here, you have a hospital which holds the ML model for disease prediction, and you have the patient who holds the medical report. They can interact in a secure inference algorithm such that at the end of it, client learns the output of the disease prediction only, and the server, that is the hospital, gets no information about the patient's record. There are several secure ML inference algorithms using MPC techniques to obtain semi-honest as well as malicious secure inference protocols. Now, semi-honest secure protocols provide this guarantee. That is, they provide guarantee against corrupt parties that follow the protocol specification, but they are only curious to learn other parties' output in the protocol interaction. Whereas the malicious setting allows security against corrupt parties that can deviate arbitrarily from the protocol specification. Some of the prior works on semi-honest security setting is CryptoNets, Delphi, CryptoFlow, to name a few. And some of the prior works in the malicious setting are Speeds, Ponytail, Overdrive. The good thing about semi-honest secure inference protocols is that they are extremely efficient. However, as we know that the security provided by them is very weak. On the other case, it's the reverse for malicious secure inference protocols. They do provide a strong security guarantee, but at the cost of efficiency. So now let's get back to the scenario that we were at. So here we have a server who is the model owner, and it's a single entity. And the server is usually reputed. Therefore, if it deviates from the protocol specification and gets caught, then the consequences can be dire because of public accountability of the server. Therefore, it is reasonable to assume that the server is semi-honest. Whereas there are multiple clients, and they can be anonymous. And there is no incentive as such for the clients to follow the protocol faithfully. And in fact, it was shown that if a malicious client is being executed on a semi-honest protocol, then it can lead to dangerous attacks. Some of the attacks are like the model extraction attacks, which allows the malicious client to learn the approximate model weights W. In fact, in a work that got published at USENIX last year, that is MUSE, it gave a very efficient model extraction attack, which was 24x to 312x faster than all prior works because it required that many fewer queries. And one good thing about this attack was that it was able to extract the model weights exactly. Therefore, this motivates us to consider the client malicious threat model, where the server is semi-honest and clients are malicious. In this work, we asked the following question: can we design client malicious secure inference protocols which are as efficient as semi-honest protocols? Well, the title of the paper is a spoiler. So in case you haven't seen it, it's good. Yeah, so in this work, we focus on neural networks, which are the prominent secure inference protocols, that you see around. And this has been the focus of almost all prior secure inference protocols. And this is the case for our work too. So neural networks comprises of alternate linear and nonlinear layers. Linear layer could be a fully connected layer or a convolution layer. And some of the examples of nonlinear layers are some of the functions that are computed that are ReLU, maxpool, etc. Now, linear layers are best represented as arithmetic circuits. Therefore, it makes sense to make use of cryptographic techniques which are efficient and more compatible with arithmetic circuits, say additive homomorphic encryption. Whereas nonlinear layers are best represented as Boolean circuits. So therefore, it makes sense to use techniques compatible with Boolean circuits, say garbled circuits. So as we make use of different techniques in the linear and the nonlinear layers, there is one subtle issue which will become clear when I present the next slide. So now let me first start with the semi-honest protocol, which are generic and most efficient in literature. So they have the following skeletal. So for the linear layers, the server has the linear layer L, and both the server and the client hold the shares of the input X. Now, as mentioned, we'll make use of additive homomorphic encryption scheme here. So client will first encrypt its share and send it to the server. The server can then first reconstruct can first obtain the encryption of reconstructed value X. Then it will obtain encryption of the computation of linear layer on this reconstructed value. And finally, it obtains the ciphertext C- corresponding to the share of the output Y of client. It will send this ciphertext to the client, and at the end of it, client will decrypt, and at the end of the computation of the linear layer, we have both parties holding shares of the output of linear layer Y, that is output Y. And now now let's come to the nonlinear layer. So now in the nonlinear layer, right now, that's the input is the output that we obtain from the linear layers. That is the arithmetic shares of output Y. Now, the problem is that here we make use of garbled circuits. So first, we need to convert it into inputs that are compatible with garbled circuits. So for this, corresponding to input share of Y0, server can easily send its labels because it is the one that created the garbled circuit. Whereas for client's input Y1, the parties need to be involved in an OT protocol such that client learns labels corresponding to input Y1. So once they obtain these values, they can run a garbled circuit to compute shares of the output of nonlinear function f on the reconstructed value and obtain the output shares of the nonlinear layer. Now, now let's see how MUSE builds on this on the previous protocol that we discussed in order to provide security guarantee against malicious clients. So here, the idea is that we'll make use of authenticated shares. For the linear layers, the change is not significant, so I'll not focus it on this talk. So let's directly jump to the nonlinear layer. So in the nonlinear layer, as mentioned, instead of shares of the output, now we will have authenticated shares. That is, we'll have the shares of Y as well as computation of one-time MAC on Y, that is alpha Y. So once you have these shares, client will obtain, client can obtain labels for its input Y1 using the OT protocol. Can it be done? Actually, no, because here client can deviate from the protocol, right? Because client is malicious, and it can send some arbitrary value of Y1 and get labels corresponding to arbitrary bits and can launch the model extraction attack that we just discussed. So for this, MUSE suggested that we make use of that novel protocol, which they call it conditional disclosure of secrets. So this protocol will output the labels for Y1 only if the MAC check is consistent. However, there is a limitation on this protocol. That is, it is computationally heavy because it makes use of leveled homomorphic encryption. Along with that, it is also communication heavy because it makes use of several authenticated beaver triples, and generating many of those is communicationally expensive. And the rest of the protocol is similar to the semi-honest protocol that we discussed. And now let's come to our protocol, that is SIMC, which is short for Secure Inference Against Malicious Clients. So our first step here is to eliminate the use of CDS protocol. So this is how we do. So again, the linear layer is similar to MUSE, so I won't be dwelling into it. But notice that the output of the linear layer is authenticated shares of the output Y. That is, you have shares of Y and shares of alpha Y. And for shares of alpha Y, I use the variable V. And now for the nonlinear layer, the inputs are the shares of the output that you obtained from the previous linear layer, that is shares of y. And additionally, the server has the MAC key alpha. So now we consider this following circuit. So in this circuit, we first reconstruct the value y, and then we compute the MAC again on the input value, that is we compute alpha y, and then we compute the output of the nonlinear function f on the reconstructed value and obtain the MAC on this output. And finally, this circuit will output shares of u, z, and t. Those shares are the ones that correspond to client. And now here, instead of making use of CDS protocol, we make use of OT protocol. And you may think like, again, the client can deviate and send some arbitrary values of y1 here. But bear with me for a couple of seconds. I'll resolve that in a minute. So here then, similar to the previous protocols, we make use of Garbled circuit in order to compute the circuit C. And the circuit C then outputs the shares for the client corresponding to variables u, z, and t. And a server in itself, because it was the one that computed the Garbled circuit, holds the corresponding shares of u, z, and t. And now we perform, at the end of the protocol, between every linear and non-linear layer, we perform this consistency check. We check whether the value v is equal to u. That is, we check if MAC u is equal to MAC v. And there is an optimization in which we can combine all these consistency checks together into one for all the linear and nonlinear layers put together. So the communication actually becomes really less. And now the server will reveal the output to the client only if this consistency check is successful. So now say if the client was to deviate from the protocol and it sends some arbitrary values for y1, and it gets some arbitrary labels. But the value that it got for u would be completely garbage, and it would not match the consistency check, and it will fail. So that is where the client will get caught, and server will not reveal its share of the output. Then the second improvement that we make over the previous protocols is computing this MACs efficiently in Garbled circuits. So for this, let me just first provide the concrete statement for the problem we are interested in. So we want to compute shares of A into B, where A is known to the garbler and B is the garbled input. So now, if we were to use a naive approach in order to compute this in Garbled circuits, the communication complexity would be order of kappa square into lambda, where kappa is the size of the field element that we are executing our protocols in, and lambda is the security parameter. So now this value B can be split into bits, can be decomposed into bits B1 to B kappa. And now let me denote the labels corresponding to bit Bi as label 0i and label 1i, corresponding to labels for bits 0 and 1 respectively. So now the garbler will first randomly sample random values R1 to R kappa, and then it will compute a decryption table D as follows. So for say bit B1 and for bit B1 equal to 0, it will first add the random value R1 with 0 and XOR it with the label corresponding to label 0 of B1. And for a bit B1 is equal to 1, it will add R1, which is the random value, to the MAC key or the garbler known input A, and it will XOR it with the label corresponding to the bit B1 is equal to 1. And it will do this for all the other remaining bits. And it will permute this entries using the permute bit of the garble that was there in the Garbled circuit corresponding to bit Bi. And now, once the evaluator gets this decryption table, it will know labels corresponding to the correct beta i's that it is currently at in the Garbled circuit computation. Then it will identify the entries corresponding to those values in the decryption table. So these are the ones highlighted in the figure. And then during that time, garbler will generate its share corresponding to the output Z, in which it will multiply the random value Ri with its bit position, that is 2 raised to I minus 1. And similarly, the evaluator will do the same with its share of values Vi. And you can verify that Z is equal to A into B. And yeah, due to time constraint, like take my word for it, it actually works out. And the communication cost here is 2 kappa square, which is order, like if security parameter is 128, so you are getting order of 64 benefit already. And now let's come to the concrete performance analysis of our protocol compared to MUSE. So now here kappa again denotes the size of the field element and lambda is the security parameter. The communication complexity of MUSE in nonlinear layer is 2d lambda plus 190 kappa lambda plus 232 kappa square. And here d denotes the number of AND gates to compute the nonlinear function f. And whereas our protocol takes just 2c lambda plus 4k kappa plus 6 kappa square, where c is less than d. And to concretely see the performance improvement, let us consider the ReLU function and set our field size to 44 bits and lambda to be 128. And we can see that SIMC performs 30x, and it's 30x more communication efficient than MUSE. Now let's see the performance, let's see the improvement results. Yeah, so here we show the performance on 2 network bandwidths. One is 584 megabytes per second, and the second is 19.2 megabytes per second. And we can see that for nonlinear layers, our protocol is 4 to 42x more efficient in network 1 compared to MUSE, and it is 2 to 16.3x more efficient in N2 setting. And for evaluating the performance of our protocol end-to-end, we consider 2 benchmarks. One is a 2-layer convolution neural network on MNIST dataset, and the second one is 7 layers CNN for Cypher10 dataset. And here, the end-to-end performance is as follows. So consider benchmark 2. MUSE takes 1,782 seconds, whereas our protocol just takes 157 seconds. And it is order of 6.2 to 11.3x more faster in N2 setting. And one interesting thing to note about SIMC is that it is more communication efficient than the state-of-the-art semi-honest protocol as well. And it is more efficient in it. So that's an interesting point that we observed in our implementation results. And then we also performed benchmarks in the pre-processing model, and we observed that our protocol was 5 to 7.4x more performant than the best-known MUSE protocol in client-malicious setting. Yeah, thank you.